Welcome, everybody. This is an area that I have been researching for quite some time. I basically started in the mid-90s. I had a project. The first project I was going to do for my PhD originally was on DNA computing. And I actually invented a scheme for universal computing using DNA chemistry. And it turned out that because of the laws of thermochemistry, the DNA computer we designed could either take forward steps or backward steps through the computation. And so in order to make any forward progress, it had to be reversible, because otherwise there would be more ways to go backwards than to go forwards, and so it would just tend to go backwards, right? So sort of motivated by this, I started studying reversible computing in more depth and turned towards electronic implementations of reversible computing, which were a lot more practical, certainly in the near term. So my talk today is going to basically be a brief survey of sort of the motivation in terms of the end of semiconductor scaling, which we just heard about. And then we can sort of break down the sources of energy dissipation in computing into energy that's dissipated at different levels in a computer design. And what we find is that a lot of the proposals for unconventional models or styles of computing are motivated by attacking energy dissipation at one or more of these levels, reducing the waste, getting rid of inefficiencies, and so forth. And I'm going to argue that's all well and good, but there's really only one physically possible unconventional paradigm that actually can potentially attack energy dissipation at all the levels in computing and reduce it by, as far as we know right now, indefinitely large factors. So if we want there to be any hope for sort of a very long-term sustainable future for performance growth in computing, reversible computing has to be a part of that. You can layer on top of that other types of unconventional computing, architectural changes, and so forth, but that reversible computing element has to be there. It's unavoidable. So I'll explain why that is, starting with the discussion of Landeros Principle, which gives sort of the fundamental physical motivation for why old-style irreversible computing is not good enough. And then I'll talk about definitions of models of reversible computing that you can derive from the fundamental thermodynamics. Oh, don't need that. And I'll survey briefly a few types of examples of implementations of reversible computing that have been proposed. And this field, I really feel, is still in its infancy. It's never received very much funding. There's never been a whole lot of attention paid to it. I think that what we can do in the future when designers turn more of their attention towards reversible computing, there's going to be a huge explosion of implementation concepts. Right now, there's a relatively small handful of them, and I'll focus on 3 general classes of implementations that have been explored in more depth than others I've seen. But there are others out there. So again, as we just heard, the motivation for this is the end of the semiconductor roadmap in terms of continued scaling of transistors. And for performance within power dissipation limits, the key figure of merit is essentially energy dissipation per operation. Well, when you look at the lowest level at the energy dissipated in locally or moderately non-locally connected logic gates, you find that there's a couple of different ways you can discuss energy dissipation. You can talk about what's the minimum energy required to switch the state of a minimum size transistor, right? So that's essentially the energy stored on the gate capacitance of that transistor. And that's this lower curve. Do we have a pointer, by the way? Okay. So this lower blue curve here is plotting the minimum gate energy. Thanks. Appreciate it. Yeah. There we go. And you can see these are figures from the International Technology Roadmap for semiconductors, which I've recently become involved with. And you can see that this is sort of asymptoting out. And the reason for that is the framers of the ITRS are aware that there are some apparent fundamental thermal limits having to do with thermal noise. So essentially, once the gate energy on a minimum size transistor gets down to the range of several tens of kT, you find that essentially there's going to inevitably be thermal fluctuations in the potential energy surface in the channel. And those are going to lead to increased leakage, which you can combat by raising device thresholds, but then that slows down the device. So then the net effect is lower device performance. So you basically get diminishing returns from shrinking transistors as you approach this energy scale. Now, that's not really the energy dissipated per bit in CMOS designs, because why? Well, in real designs, transistors tend not to be minimum size. They tend to be sized for best performance, depending on what logic network they're driving. So a typical transistor width could be as much as 10 or 20 times minimum width. In addition to this, you've got parasitic capacitances in the PN junctions of the transistor. You have multiple transistors in each logic gate that are being driven by a given signal. A given signal will tend to fan out towards several logic gates. And then there's wire capacitance, depending on the length of the wire and how local the circuit is. But when you multiply all these factors together, you get hundreds of times more energy stored in a typical logic node than is in the minimum sized transistor gate itself. And this is kind of inevitable from the way we design circuits today. I mean, you can't really, there's no sort of magical way to eliminate all of those overheads. Even if you try going to like a cellular automata architecture where all the connections are local, well, you still need to communicate information over longer distances to interact data that does not happen to be located next to each other. And so it doesn't really help at a systems engineering level to make those kind of architectural changes. So anyway, the end result is that the total energy dissipated is some factor like 500 or so times the minimum transistor energy. And so that's leveling off. And we see that this is leveling off at, even though this is a level of a few eV, this is leveling off at a kilo electron volt, which is essentially reflecting that on the complete circuit node distributed to several logic gates, there's going to be several thousand electrons sitting there, at a volt or so. And that's kind of inevitable. One electron is not going to be enough to sort of cover that whole structure. And so when we, essentially when you ground a circuit node, you're dissipating all that keV of stored electrical energy to heat. Okay, and so we really want to avoid that. And for a long time, people said, oh, well, reversible computing is not relevant because we're so far from Landeros Principle. Why do we care? But look, these multipliers are real. It's not just, thermal limits that are important. It's this large factor, larger than thermal limit amount of energy per circuit node that we inevitably are going to have. We have to try to recycle that energy, or there's no way we're going to get below this keV level, okay? At least not with, ordinary electronics, okay? You can try to move to something else like superconducting or optical, and I'll say a little bit more about those later. So you really have to begin recycling circuit energies, and then that leads to the concept of reversible computing, because you can only completely recover or approach full recovery of signal energies if your computation is logically reversible, and I'll explain why that is in a bit. So sort of my general argument is that we're very quickly approaching the end of the roadmap, and really only reversible computing can take us from there far into the future, indefinitely far, even below the Landauer limit, and we'll talk about why that is. So the fact that we have in conventional technology these apparent limits on energy efficiency, it has severe implications for supercomputing, which is why Sandia is interested in this area, frankly, because they do a lot of supercomputing at Sandia. They're always trying to improve the performance and capability of their machines. Right now, a lot of people in our center are involved with the exascale computing program, which is aiming to get an exaflops scale supercomputer by around 2021, so about 4 more years. And it's a very aggressive schedule, and it's not really completely clear if we're really going to hit the power performance targets that we want. But in any case, that's an exaflop, so we'll probably get there. That you can do almost with today's technology. But then, even at the end of the semiconductor roadmap, you're only going to be able to get a little bit beyond that at reasonable power levels, right? And then if you want to ask how much power will it take to do a zettaflop, well, even at the end of the roadmap, we're talking about more than a gigawatt for a supercomputer. I mean, that's like, comparable to Hoover Dam, right, in terms of total power load. And that's optimistic. That's even ignoring the overhead for interconnects and cooling systems and all of that, which is real overhead that has to be accounted for. And then, even if you say, well, maybe we can reduce dissipation per operation to near that thermal noise limit and somehow get rid of all the architectural overheads I just mentioned, even then we're still, it's going to be more than a megawatt. I think lots of people would be happy with a megawatt scale zettaflop computer, but what if you want to go beyond that, right? Even more flops. And so you find that, basically the future of computing is going to halt forever unless we do irreversible computing. That's the only thing that can take us into this red wedge. And as far as we know, indefinitely far into it. Okay, so I feel like, we've really got to start paying attention to this, right? If we don't, it's sort of at our peril, of the whole industry is going to stagnate. And there's essentially no question about this physically, unless we master this new technology. All right, so this is sort of my slide giving an overview of energy dissipation at different scales in computing and how this relates to unconventional computing paradigms. And people like to, point out, they say, oh, reversible computing is only affecting the logic gate, but we have all these overheads at other levels, so why are we doing it? And there are overheads, certainly. Just cooling a data center is, a significant chunk of total power consumption, and, it's hard to eliminate the cooling overhead. You can try to site your data center in Iceland or something, or, an extreme example would be in a pole at the moon where the permanently shaded craters are like 30, 40 Kelvin. But, short of crazy things like that, there's not much you can do to improve the efficiency of cooling systems. Then there's networking. A huge amount of the power consumption of modern data centers and supercomputers is in the interconnects between nodes. And then memory systems are a big chunk, not only the energy to keep the memory refreshed if it's DRAM, but also the I/O to provide the memory bandwidth that applications demand. And so for things like networking and even more local interconnects, optical is being pushed as a solution. There's also processing and memory type architectures that try to locate more of the processing closer to the memory. Those things are quite helpful. Optical's even being looked at for board level and within packages, and some crazy far out people are even looking at optical in between transistors, right? And we don't really know how to do that efficiently yet, but people are looking at that. So that's nice. There's also overheads due to the architecture itself. So, a traditional microprocessor has an instruction set, and a lot of the gate operations in that microprocessor are just going to interpreting the instruction set, scheduling instructions, managing various queues and buffers in the microarchitecture, and so on. And so if you get rid of the instruction set and you go to some lower level, like you configure an FPGA, or you have some specialized architecture like a GPU or a neural architecture, or at the extreme is you make a full custom ASIC specifically for your application, you can gain quite a bit of performance, 2 or 3 orders of magnitude even, compared to a microprocessor. And that's great, but it's a limited, finite sort of gain that you can get there. Eventually, those low-hanging fruit will be picked. All of the important kernels will be compiled into, ASICs that are part of these heterogeneous systems that need them, and you won't get any further gains beyond that. Then there's the wiring themselves. I talked about that already as a factor in energy dissipation, and one thing that's been looked at is low voltage switches, although there hasn't been any great empirical success yet so far as I've heard in terms of actually being able to get really steep subthreshold slopes and beyond the limit for field effect transistors. But people are still trying, But the danger of lowering the signal energy is what I just mentioned, this thermal noise limit, right? And I think that's going to still cause problems even in various low voltage device technologies. So I don't think that they're going to give you any sort of magical way around that limit. Then there's the overheads of logic gate structures themselves. And we've had a lot of generations of development of CMOS technology. And I think the gate designs are about as good as we're going to get unless we go to adiabatic circuits, which we'll talk about. And then I already mentioned how there's this thermal noise limit on the gate energies themselves. So they're not going to continue getting smaller much longer. Now, people say, oh, why are we doing reversible computing? It's just helping the logic gates. What about all these higher levels? Well, they also can be reduced by reversible computing. Communication networks can use reversible methods to charge up interconnect lines. Memory devices, you can define memory interfaces that are reversible, and you can do that reversibly as well. Leakage is always a problem for reversible as well as irreversible technology. But if you find a good non-volatile memory device that's not dissipating a lot of energy, doesn't need a lot of active refreshing, you can operate that in a reversible mode and reduce power dissipation in the memory system, the memory interface, and all of that, right? So there's no reason to think that you can't apply reversible computing at all of these levels, right? There may be unique issues and complexities at each of the levels, but as far as we know, we can apply it everywhere. It's sort of a universal principle in computing and digital data manipulation in general. I'm just going to very quickly show a couple of slides that are just here to sort of illustrate that work is being done at Sandia at a number of these levels for different kinds of unconventional technology. So this is a slide on, some work on optical systems at Sandia. There's been a lot of work on silicon photonics, where optical devices are integrated on chip, and processes that are compatible with CMOS technology. And this isn't my specialty, so I'm not going to say a lot about this because frankly I don't know a lot other than what is on the slide that you can read for yourself. But there is a fair bit of work being done at Sandia. There's strong belief that this is going to become increasingly important for interconnect and high-performance computing. And it's expected that exascale systems will contain a fair amount of optical hardware. So another area being worked on at Sandia is neural computing. We see sort of neural computing, it's a class of accelerators that are not necessarily going to speed up all computations, but for computations that have a significant learning component that's needed, or pattern recognition, something that can be compiled into a neural framework efficiently. Neural hardware can potentially give you some of these, constant factor energy benefits compared to running a similar algorithm on a general purpose processor. So, there's a number of facets to the interest in neural computing at Sandia. One major project at Sandia that just finished is the HANA Grand Challenge. And there's a number of facets to that project. They spent a fair bit of time looking at crossbar architectures, developing new spiking neural network architectures, looking at low-level devices for speeding up neural computing, such as memristors and electrochemical transistors. And so there's a lot of interesting work there, and there's some references down there. By the way, are the slides going to be provided or posted? Yeah, so if anyone needs to see those references, they can check them out later.
On your previous slide, you mentioned CMOS.
Yeah.
You're also working on the silicon and sapphire stuff a little truer. Can you talk about that?
That's not my area, so I don't really know anything about that anyway, so not going to talk about that. I'll talk a little bit about CMOS, a little bit about superconducting, and a little bit of other stuff. Okay, so that was all I was going to say about other unconventional computing approaches besides reversible computing. As you can tell, I'm a big fan of reversible computing, and so this is what I'm going to focus on. First, like a brief primer on thermodynamics of information. Sort of the modern physics understanding of entropy is it's essentially statistical uncertainty about the microstate of a physical system. And by microstate, we mean you can refer to a set of distinguishable quantum states of the system as being the microstates. And physics as we know it is bijective. In the case of quantum theory, it's believed to be unitary. It's doing essentially a one-to-one transformation in the space of state vectors. And because of that, any initial probability distribution over the microstates, if you tracked the exact unitary evolution of the quantum system, you'd get the same probabilities coming out. You've got a one-to-one map from old states to new states. So there's no change in entropy at that level. Neither increases nor decreases. And the fact that this relationship is one-to-one is, in fact, it's the reason why the second law of thermodynamics is true. Because if states did not map one-to-one on the new states, you could have two states with some probabilities associated with them that merge into a single state. And when that happens, the probabilities combine, but the entropy associated with that state will always be less if these are non-zero probabilities. And so entropy would decrease spontaneously in those cases. And since this never happens empirically, we essentially know that whatever fundamental laws of physics are, they have to be injective. Now, why can entropy increase? Well, entropy increase can be understood. It's simply a consequence of the fact that we can't perfectly track the evolution of a system. We can't keep track of all the correlations that arise when systems become entangled with each other, and in general when they interact with each other. And also we don't know the laws of physics exactly. We don't know the fundamental constants to infinite precision. So, given that you don't know exactly what transformation is happening, even though we know the underlying transformation is one-to-one, since we don't know exactly what one-to-one transformation is happening, the probability distribution ends up getting more fuzzy over time. So in a sense, the second law of thermodynamics can be understood as it's essentially just a consequence of injectivity of microphysics. And the fact that entropy can increase is a consequence of the fact that we have imperfect knowledge about physics and a perfect ability to track the state of a system. Now, some people say, oh, that's great, that's physical entropy, but what about computational entropy? Isn't that something different? Information entropy, Shannon entropy, that's something different. That's about logical values and knowledge about logical states. Well, it's really not different, because what is a computational state? It's just an aggregate or a set of physical states that we consider equivalent for computational purposes, right? That definition goes back to Shannon, but I don't think anyone could sensibly question that definition of what a computational state is. And it turns out that, given that we can group states, you can break down the total entropy of the system using the chain rule of conditional entropy, and you can say the total entropy, it's just the entropy of the probability distribution over your computational states plus the conditional entropy of the physical state given the computational state, right? So it's essentially computational entropy plus the physical entropy if the computational state were known. That is total entropy, all right? And this is just a theorem, right? There's a theorem of conditional entropy that tells you this. This is just a little visualization I came up with to help understand this, So if this is a probability distribution over states, and the thickness of the line is the probability, and the length is essentially the log of 1 over probability, then, if you group states together, that's just sort of rearranging this tree, but it's not changing the total area of the branches, which is the total entropy, all right? So, there's essentially no question about this. Physical entropy it's just a part of, computational entropy is just a part of the total physical entropy of the system. There's no way around that, okay? So this, in turn, leads directly to Landeros Principle. Okay, so you have computational states that are just sets of physical states. So let's say you have a bit, 2 possible computational states, and you want to erase the bit. So you want the new state to now be, say, 0 unconditionally, whether or not the previous state was 0 or 1. Well, essentially you're merging then 2 sets of physical states into a single computational state. And because the underlying dynamics has to be bijective, and because the total entropy is always exactly computational entropy plus non-computational entropy, what happens when you do this merger is the computational entropy has to decrease because you're combining probabilities together. And so the non-computational entropy has to increase, right? So in this example, we've lost 1 bit of computational entropy because each of these states had probability 0.5. And so we have to gain 1 bit's worth of non-computational entropy. It's just falls directly out of this trivial algebra, okay? All right, so I never can understand why people question Landeros Principle, because all this stuff is just so dead simple. There are some subtleties, maybe, that if you don't understand, they can trip you up. So what are we talking about in Landeros Principle when we say we have computational entropy? Well, really, information in a computer, you may not consider it entropy in the strict sense, because in a sense it's known information. Information that you've computed from some inputs you've provided is sort of logically implied by the input you provided. It's not unknown information in that sense. But Landeros Principle still applies. It's still information. And so a way that you can model these types of situations is some input comes in, you do some computation on it, which here I'm modeling with a controlled NOT operator that just XORs the first bit into the second one. And, with this previous slide, we saw we can move information back and forth between the computational and non-computational domains. That just sort of depends on where you draw the boundaries of your computational states. And whoops. So there's no reason you can't sort of take this computed bit and move it into the environment with some reversible transformation. But the thing is about the environment, when you say it's non-computational, that sort of implies it's this uncontrolled environment, right? So we're not sort of explicitly manipulating the states. It's a thermal environment. It's subject to all kinds of noise. You can have some random mixing of states that happens in the environment. So you can't assume that any correlation present in the environment will be maintained. I mean, even if it's maintained by the raw physics, we can't track that evolution, right? We're not able to track the correlations once they escape into a thermal environment, right? So that's essentially why entropy must increase when you move it out of a computer, because you've taken something that was just a correlated bit. It wasn't true entropy, really. You moved into the environment. Now it becomes randomized. So that's irreversible, okay? So there's no way around that. I was just at a talk on thermodynamics of, a workshop on thermodynamics of computation at Santa Fe Institute a few weeks ago. And, you know, the thermodynamicists there, I was surprised they didn't seem to understand this. But then after I showed the slide, they got real quiet. And, you know, they seemed to understand it after that. All right. Now, here's the difference in reversible computing. You have a computed bit. Now, instead of pushing it out into the environment, you simply do another computation on that bit, which one trivial way to do this is just the time reverse of the original computation that produced that bit, if that was a reversible computation, and then that restores that bit to some standard state, say here 0, right? So now this is sort of free memory. You've temporarily used some memory to compute some result, and then you undo that, and now you've got free memory again, which you can reuse for another computation. And this is sort of the most trivial example, but you can do this with arbitrarily complex computations, and that's reversible computing. And you don't care what's happening in the environment because you haven't pushed any of your digital bits out into the environment, and the environment can initially be in a random state, and then it can re-randomize that state all at once, and then you don't care because it's not affecting the entropy in your computational system. If this is already at maximum entropy, its entropy is not increasing further. So you can theoretically get by with no entropy increase in these types of structures. And this was essentially the basic concept behind this was first discovered by Bennett in '73. I mean, Landau sort of anticipated it, but didn't fully understand that it could work. And then Bennett showed how it could work at a logical level. So, all right, that's sort of a preview. So now let's see if we can formalize this notion of reversible computing a little more. I want to define what reversible computing is. Well, fundamentally, what are we doing when we're developing reversible computing? We're answering the question of what are the conditions that must be met at the logical level in a computer in order to avoid ejecting entropy from the computational state. This thing that we saw happened, you know, in Landeros Principle, where we had some entropy that was originally in the computational state, and then we pushed it out in the environment, and now it's in the non-computational state where you can't get it back. You can't uncompute it at that point. All right. So Landauers' original paper was trying to sort of define some intuitive notion for what needed to be the case to avoid this entropy increase. And, you know, he came up with this thing he called logical reversibility. He said, let's map one-to-one the whole space of, say, 2 to the n possible states for an n-bit device. Let's map that whole set of states one-to-one onto new states. And then there's no merging of states, and so there doesn't have to be any entropy increase. Okay, well, that's fine for what it is, but it turns out that's, although it's a sufficient condition for physical reversibility, it's not the least restrictive possible sufficient condition. So it's not strictly a necessary condition. All right, so to show why, we have to sort of carefully define some concepts. You know, a device I think of as a physical artifact that can perform computational operations. An operation itself, it's just a map from old state to new state. You can have stochastic maps in the theory of stochastic devices. I don't get into that. I'm just talking about deterministic devices at this level, although the theory could be extended to non-deterministic or stochastic operations. And then this is important. The notion of a computation that we're going to use, it's not just some operation we're performing, but it's also a statistical operating context. And you have to have that really to even define quantities like entropy. You have to have a probability distribution to give any kind of precise definition of entropy. So, so given that you're performing some operation with some set of initial state probabilities, we can say, okay, that's a computation, or you can think of it as a computational scenario. And we're going to study entropy ejection in those scenarios. So again, this is Landauers' original definition. It's sort of the popular definition in the computer science community of what reversible operation is. And like I said, it's this one-to-one map from old state to new state. And indeed, you know, if you want to define an operation and say that entropy is not ejected for that operation, no matter what the initial probabilities are, then this is the only way to do it. All right, and that's true. And then that leads to this whole traditional theory of reversible computing based on some things you might have heard of, like Fredkin gates and Toffoli gates and controlled knot gates. And you know, there's a very nice, beautiful theory of what you can build out of those things. And it's been widely used in quantum computing because quantum computing needs this sort of full reversibility for quantum algorithms to work. And that's all very well and good. But if the goal is just to save energy in computation, this turns out that's not the most general model of reversible operations, even classical reversible operations. So here's the definition I propose, or you can say, you know, we can use this definition alongside the other one, but this is a definition of logically reversible computations, where a computation now includes the operation being performed and the statistical operating context, the probability distribution over initial states. Well, it turns out all that we have to do to avoid ejecting entropy is to one-to-one transform just the states that have non-zero probability. Some states can have zero probability. Why can states have zero probability? Well, we do this in computing all the time. We have functions that have preconditions that have to be met in order for that function to operate in an error-free way. And then we ensure by design for that function in the context of a larger program or for some digital subsystem within the context of a larger system, you know, that those conditions are met, right? This is routinely done, right? We know as designers how to ensure that preconditions are met, right? So all that you have to do at the logical level to avoid entropy ejection from the computational state is that the states that will actually arise will get transformed one-to-one. And if the states that don't ever arise would be mapped onto some of the same states, that's okay, because if those states have no probability associated with them, there's no entropy associated with them. There's no contribution to entropy from those states. And so you find, you know, the total entropy of the probability distribution before and after the transformation is the same. And that is sufficient to avoid Landeros Principle. And we'll see concrete examples of hardware for this in a second. So the rest of this is just sort of defining some terminology, but that's the key insight. And it seems like a trivial thing to notice, but the fact that this has not been made explicit in reversible computing theory in the past has led to huge amounts of confusion. So, you know, engineers will realize this is true sort of intuitively and go and design devices that are perfectly fine as reversible devices, and then the CS theorists will come along and say, wait, that's not a reversible device because it's not performing a one-to-one transformation of the whole input space. But they don't realize they're using an overly restrictive definition of what a reversible operation is. For practical purposes, for engineering purposes, this is the right definition, okay? And so you can, it turns out you can drastically simulate designs for reversible machines by taking advantage of this definition. So it allows you to do different kinds of reversible operations that may be much simpler to implement. They're still adequate for performing whatever computation you want to do. And so you build out of those.
So basically just introducing a nil.
A what? Introducing a
nil. True, false, and nil.
True, false, and, you know, not applicable or undefined or don't care. You could call it a don't care state.
No, but there's like one Pratt, for instance, defines as a nil. Then you do an algebra true, false, nil, and then it works.
Yeah, I mean, yeah, there are ways to represent this algebraically, certainly.
Well, that's important.
Oh, yeah.
You want your logic to be compatible with your arithmetic.
Right, and, you know, I would love for people to go and develop a whole algebraic theory of, you know, how you compose these things, and that would be.
One Pratt, for instance, is one example.
Okay.
He's in this building.
Okay, well, he should hear this probably. Fortunately, it's being recorded, so you can send him the YouTube link.
I will see it.
Okay, so that's sort of generalized reversible computing theory, and now let's talk about circuits. There's a whole history of development of this concept of adiabatic circuits. And it really started with Fredkin and Toffoli. They did a DARPA pre-proposal, actually, way back in 1978, where they sort of proposed this idea that let's shuttle charge around between inductors and capacitors, and we'll use switches to control where the charge goes, and control the timing of those very carefully. And so that was sort of the beginnings of a concept, but it wasn't fully fleshed out as to how you would do logic with that. Seitz at Caltech did some more work on this, but his circuits were not completely adiabatic. He didn't realize you could do universal computing with those circuits. And then there were some further developments at the Physics of Computation workshop in '92. Basically, several groups independently came up with a way that you could do arbitrary combinational logic in CMOS and adiabatic circuits, but they weren't sure you could do sequential logic yet. Then Saeed Yunus and Tom Knight, who was, Tom was my advisor at MIT, came up with the first sort of fully adiabatic general sequential circuit technique. So basically any sequential reversible operation or state machine that you could define, you could then implement that in adiabatic CMOS in a sort of systematic way. This technique took a lot of transistors, and they came up with a simpler version of it in '94 called SCRL for split level charge recovery logic. It turned out SCRL had a bug, which I discovered during my dissertation work. It's easy to fix the bug, but we developed several chips before we actually found the bug. So these chips, we thought they were going to be fully adiabatic, and they weren't. But we know how to fix the bug now, so they could be redone. But these were...
Mm-hmm. Same story.
Yeah.
So it's older too.
What's that?
Boole was when Boole came out with Boolean logic, people complained of the counterexample.
Right.
Then if you put in a nil, it works.
Mm-hmm.
They knew that then.
Yeah.
So has an older history.
Yeah. I gave one of my talks once at MVL, International Symposium on Multi-Valued Logic. So that community is interested in this stuff. But anyway, so yeah, these were just proof of concept chips anyway. These were not designed to be particularly efficient. Pendulum is sort of a MIPS style CPU using an instruction set, reversible instruction set that I helped to develop. Flat top is sort of a cellular automaton architecture that in principle is universal, that had a very simple cell design. And there was a memory chip, and TIC was just a irreversible implementation of the pendulum ISA. So anyway, we made some test chips, and there were some bugs in them, but it was sort of a beginning. So here's the principle for how adiabatic circuits work from a sort of electrical engineering perspective. You can think of it as it's just the difference between charging from a constant voltage source and charging from a constant current source. And in this diagram, you can imagine there's some switches not shown that turn the current source on and off at specific times. But in both cases, let's say we want to move some charge Q onto some capacitor, all right? And the conventional analysis, for energy dissipation is just essentially half of the total energy coming from the supply gets dissipated when you charge up the capacitor, and half will get dissipated when you discharge it. So it's like 1/2 CV squared in each step. And for adiabatic charging with a constant current, it's just simple algebra. You find that the dissipation for moving that amount of charge is it's CV squared multiplied by this factor RC over T, which is essentially scaling down as the transition time becomes larger. And this is sort of just reflecting the fact that the quality factor of the circuit is higher at lower frequencies. So you can gain an advantage in energy dissipation from adiabatic charging, and that's all well and good. But then how do you do logic with that? Well, here's where the generalized reversible computing theory starts to be useful, because you can actually describe at a logical level what a transistor is doing, and you can see why there's a regime in which what the transistor is doing is reversible, logically reversible according to the generalized definition, which traditional reversible computing theory didn't handle at all. So this is just a simple sequence of operation. I'll just explain it with reference to the picture. We start out with some output node B that's initially 0, and a driving node D that's also initially 0. And we have a gate node A that, in the first step, you can set A to some value, right? A new value, 0 or 1. And that's going to turn this transistor on or not. We'll assume that the ones here are strong ones and the ones here are weak ones, so that, we don't hit the threshold of that transistor when we're charging. But anyways, this transistor is either on or off. Then the driving signal here just ramps up over some period of time, and this is the T from the previous slide, ramps up to some new level, right? And so B is connected to the driving node, and A is turned on, then it will follow the driving node, with some small lag, depending on how fast you do this, but it'll follow it up to that new level. And, that's an adiabatic transition. That happens with, just that small amount of energy dissipation determined by how fast you do the charging. And you can undo that, you can ramp the driving node back down. And when you look at what's happening logically, you can see that most of the input states get mapped one-to-one on the output states, but there are cases that don't. So for example, if B was not initially 0, if that precondition was not met, and then you happen to set A to 1, right, and D is initially 0, well, now you'll have a sudden flow of current across the transistor because you've got a voltage drop across it, and that's irreversible physically, and this is logically irreversible as well. So what you do is you ensure this state has 0 probability, and then there's no entropy associated with it, and no energy gets dissipated when you turn that transistor on, okay? So, so that sort of connects the fundamental Landauer theory of reversibility with the physics of adiabatic circuits, right? And so this is why adiabatic circuits can be adiabatic, is because they're doing generalized reversible operations at the logical level. And that's essential, you can't, there's no way physically, that you could do a many-to-one transformation if these all have non-zero probabilities, okay? So, and that's guaranteed by fundamental physics, right? So if you believe fundamental physics, you already know there's no way to do, to implement that operation adiabatically if it's not logically reversible in this generalized sense. Yeah, this example is just a pass gate. It's a single transistor. And the reason I start with a single transistor is because obviously you can't build any larger adiabatic circuits if you can't operate even a single transistor adiabatically, right? Because any larger circuit is just an assemblage of transistors. And everything you do with each of those transistors has to be adiabatic in order for the whole circuit to be adiabatic. When I was at UF, my students developed a simulator in Java. It was a sort of simple, discrete time simulator that could check sort of an arbitrary CMOS circuit and an arbitrary set of waveforms with discrete levels and tell you, is that an adiabatic operation sequence for that circuit? It's a very useful little tool. We're probably going to try to re-implement that in modern tools in my current project.
Think of that as the nil state. You want 3 states.
Yeah,
also nil. This is the nil.
There's a no information state essentially, right? It's the default state before you do the operation.
It's like some full address has true, false, nil, pass, propagate, kill, propagate.
Mm-hmm. Yeah, that's a way to think about it.
Yeah, I don't same thing. It's 3 level basically.
Yeah, well, in that example, we didn't actually have 3 levels, but you could think of it as a third condition, which is, this is a condition where there's no information in the bit. It's always 0, right? All right, so that was just a reversible copy operation. It essentially copied A to B logically, but you can also do more complicated operations. So here's a conditionally reversible OR operation. Okay, we just have 2 parallel charging paths. And here I'm using transmission gates in each of the charging paths so we don't have to worry about the voltage levels. They can go full swing. And the sequence of operation is similar. We have some driving node that's initially 0, and the output node's initially 0. And then the inputs A and B go to new logical levels. These transmission gates get turned on or off, respectively. And then D transitions, and if A is on or B is on, Q will follow D and transition to the new value, which will then be logically equal to A or B. Right? So there's an OR gate using just a few CMOS transistors. You actually need 8 and not 4 because this is just one of the polarities of the output, and if you want dual rail everywhere, you need the other version of it also. But it's a very simple thing conceptually, right? And this was actually invented long, long ago. So, some of the very earliest implementation schemes for reversible computing, some of the early superconducting schemes and early nanomechanical schemes, and Seiss's work basically use this concept as well. I mean, lots of people sort of independently discovered this from the engineering world. And yet, a lot of the CS theorists would say, wait, how is that reversible computing? It's not doing a Toffoli gate. Yeah, I don't understand this, blah, blah. So now we know how to understand it. I mean, I would argue some people have known all along how to understand this, but I'm trying to sort of bring it to light in the wider community as to why this is logically reversible. Okay, it's logically reversible assuming certain preconditions are met, which is all that's needed. Okay. And why is this relevant? Like I said, this creates a lot of confusion, the fact that this hadn't been previously recognized. So an example of that, there was a paper in Nature Communications just last year in 2016, where some physicists, they built and tested this very simple OR gate that was conceptually the same as this, except it was mechanical. It used cantilevers and barriers instead of electrical signals. And, they measured the dissipation and showed, it's less than KT, it's less than Landauers' limit. Reversible computing theory must be wrong. Well, it was reversible. It was doing exactly one of these conditionally reversible operations. And they just didn't realize it was reversible because they were reading the CS theorists' definition of what a reversible operation was, right? So basically, these incorrect definitions really cause a lot of damage for the whole field because they create these misunderstandings that lead people to think that the fundamental theory is wrong, whereas I would say the traditional theory was incomplete, and the correct theory is not wrong. That's sort of a redundant statement, but yeah. Correct theory is correct. Anyway, this was all from a logic style I invented around 2000 called two-level for two-level adiabatic logic. It was also a sequential logic style, and in fact, it was the simplest sequential style in the sense that you could combine logic and latching functions into a single structure and save time in a clock cycle by not having to do them separately. And so this is an example of a shift register in two-level. Let me see if I can play the animation real quick. Not sure if this will work, but well, you don't really need the animation. This is kind of showing you what is happening here. There's just a pulse that travels down this line of, these are buffer stages, and they look symmetrical because they are. They're essentially doing the same thing in both directions. They're computing a copy of the bit in the forwards direction, and then they're decomputing the old copy from the new one in the reverse direction. So you get a wave of activity that essentially propagates down this pipeline. And so this is a truly pipeline circuit. Every 4 phases, you can have a new wave of information flowing through the circuit. You can do logic in each of these stages. In this example, these are just buffer stages, so there's no logic happening, but you could do logic in each stage, so you could basically get any sort of fully pipelined sequential circuit in this style with 4 phases of clocks. We got some very nice simulation results. So we actually simulated this using a high-level MOSFET model in TSMC 180 nanometer technology, which we had the libraries for. This was work at UF. Actually, the simulations were done in 2004. And these are graphs that shows power versus frequency. And for a conventional irreversible CMOS, they're just power's proportional to frequency. Frequency is decreasing to the right, and power is decreasing as you go down. So you get this one-to-one proportionality between power and frequency, which is unsurprising because the energy per circuit node is the same no matter what the frequency is, and you're just dissipating that energy more or less often depending on how frequently you cycle the circuit node. For adiabatic circuits, power is quadratic in frequency because as you slow down those adiabatic transitions, the energy dissipated per transition is decreasing, and also you're doing the transitions less often, so you get this double slope here, and that's exactly what we got from our simulations. This only goes down so far because eventually you run into leakage, limitations of the transistors due to leakage. But notice the best data point we got was 1 electron volt of energy dissipated per transistor per clock cycle. And that's amazing because that is at least for close to 5 orders of magnitude less than the actual energy stored on each circuit node, okay? So, so we're getting away with dissipating only, hundredth of a percent or 10th of a percent of, no, 100th of a percent or less of the energy. So that's pretty good. Now that was sort of assuming ideal power supplies, rail drivers for those ramps. And if you build a real resonator, you're not gonna get a Q that's 10,000 or 100,000. More likely you'll get a Q, even using good components, that's maybe tens or hundreds. We had a project for a while at UF where we thought, okay, maybe let's build a resonator with MEMS components, electromechanical resonators, because those can have Qs in the thousands, and maybe that's a good combination. But that turned out, we didn't have much funding for that project, and it turned out to be too hard to do within the scope of the funding we had. But maybe we're trying again at some point. Here's a simpler approach you can do in the meantime. You could build a trapezoidal waveform generator just by essentially, you just need resonators for the fundamental frequencies, fundamental frequency and the harmonics for that signal. So with 6 terms in a Fourier series, or six harmonics, you can get within 1 or 2% of the ideal waveform. You can't really see it there, but there's an ideal waveform, and then there's the actual Fourier series, and they're so close together you can't really tell them apart. And this is an exaggerated error, so you can see the vertical scale there. So that's nice. You can potentially build a resonator like that just by having parallel bandpass filters, notch filters essentially for these for those fundamental frequencies. So if you can tune these components precisely enough, and then you can excite this whole circuit with a waveform of the right shape to get the right relative amplitudes for all the frequency components, then in principle you can generate that whole waveform resonantly, which with some Q that's determined by the parasitics of the structure, right? And so we've got a project right now where we're gonna try to actually build a resonator like this with sort of the best available components with some sort of custom packaging, and just see how high a Q we can get for the trapezoidal waveform. And then that will be well suited for actually driving a real demonstration circuit. And our goal would be to show that you can actually save energy in practice for useful combinational circuits. Like we'll build things like counters and so on, and show you can run a counter with maybe 10 to 100 times less energy per cycle than you can do with any conventional CMOS. That's what we hope to show. Okay, so that's adiabatic CMOS. And I'm about out of time, aren't I? So go on a little longer. Okay, I won't spend a lot of time on this slide. This is just sort of an introductory slide on reversible superconducting circuits. I'm not going to try to explain in detail how they work because I'm still learning about this area myself. So I'm still fuzzy on some of the details, but basically these have been in development since the late 70s. Concepts for how to do adiabatic operations using superconducting circuits. And the degrees of freedom are different in a superconducting circuit. You work with phase differences and loops and magnetic fields and current pulses. And so it's a different domain than CMOS. But a lot of the principles are similar. So you still need external control lines like an adiabatic CMOS, and there's overheads associated with those. One very new project, this was an idea I just came up with last year, or it's something I've been thinking about since the early 2000s, but I sort of finally figured out how to do this last year, is a sort of asynchronous ballistic style of reversible computing. And this is something that's never really been described before, but the goal is to define devices that operate reversibly, but where the inputs arrive at different times instead of at the same time. And that's to prevent input signals from sort of interfering with each other and increasing uncertainty of the relative timing when they interact. And they have to have state as a consequence in order to do logic. And I came up with a simple set of devices that appears to be universal, or is universal for reversible computing and irreversible computing embedded within reversible computing. And so here's an example of, this is essentially doing an AND operation. We have a pulse that comes in here on this control line, bounces off this gate of what I called a toggle barrier, toggles at state, and then you have a data pulse that comes in here and either passes through or gets routed around to this other path. So the net effect of this, if it's prepared in the correct initial state, is it gives you a logical AND of the inputs and some other stuff. But the inputs don't have to arrive at the same time. In fact, they should not arrive at the same time. So this is sort of easier to work with. It's hard to coordinate timing in a ballistic computing system. And so here we just don't try to coordinate timing. This slide has a lot of words. I'm not going to go through all that, but just to say that we're trying to implement this with superconducting circuits. It seems appropriate. Pardon? Helium temperatures are good for like niobium and other materials. And there's been some nice work recently showing that indeed you can get nearly elastic interactions of, so fluxons are these units of signal in superconducting circuits. They're essentially a quantum of magnetic flux. And in this work, they basically showed that you can do things like buffers and NOT gates that only dissipate a few percent of the signal energy when a pulse passes through the device. And so we're hoping to build our asynchronous reversible devices in a similar fashion. So flux quanta or fluxons can come into the device, interact with it, possibly change its state reversibly, and come out. And most of that energy is preserved. And then the idea of that is you could go through many stages of logic before you have to do resynchronization and signal level restoration. But the point is that you lower the overheads needed to do things reversibly. So you don't have to clock every stage. This is an even more far out concept, and these ideas go back to the early 90s in some work by Eric Drexler. But this is a group out of the Institute for Molecular Manufacturing, and they actually figured out a way that you could do reversible logic using only rotary bearings. So this is to eliminate all sliding interfaces. And the rotary bearings are nice because you can implement them with single atomic bonds. Okay, so this is a single carbine bond at the top and bottom of this rotor here. And they analyzed frictional coefficients in that structure and got some extremely small values. So they did some detailed molecular dynamics simulations and got simulated dissipation of 4 times 10 to the minus 26 joules per cycle at 100 megahertz. Well, that's 74,000 times lower than the Landauer limit for irreversible operations. So it really shows the potential benefit of reversible computing. And notice the speed is still respectable. In fact, you could run this structure probably at a gigahertz and it would still work, although the dissipation would be somewhat larger, but probably still thousands of times better than Landauer's limit. Let me actually see if I can play this animation so you can get a feel for what's happening there. And the logical structure, this is just a shift register again, and the logical structure is essentially the same as that electrical one I showed earlier. But all the steps here are mechanical, and they're all reversible. And this whole thing is supposed to be driven by, a set of cam wheels. All right. So, I don't think they've done a complete mechanical analysis of the entire structure with all of the possible modes included. So, this results may be somewhat optimistic, but I still think they nicely illustrate that we are still very far from any fundamental limits on how efficient reversible computing can be. Sorry. Yeah, you can kind of get a feel for the length scale from this diagram. So, you can see that this is just, I keep losing the button here. This structure is, what's that about, nanometer or so thick, just a few atomic diameters thick, and the total distance between the rotors, maybe that's 10 or 20 nanometers or something. Okay, so this is a pretty small structure, right? And at the larger scale, this is probably hundreds of nanometers long in this lock structure. Basically, the operation of this is one of those blue bars can be shifted out of position, but only one of them at a time, just because of the geometry of the structure. So that's essentially your bit storage element. So that's very beautiful stuff, I think. All right, so in conclusion, we have this problem that the raw performance within any reasonable power constraints of computing is approaching some limits that ultimately are rooted in very fundamental thermodynamic issues. And various kinds of unconventional computing concepts aim to reduce inefficiencies at different levels in computing. And that's all great, but if you only attack one or a few of the levels, you can only reduce energy dissipation by a certain factor. And also there's the bottommost level of the fundamental thermal limits of individual devices. And if you can't decrease those more than a certain factor, that's going to fundamentally limit the improvements you can get. And so the only way that you could possibly continue improving over many orders of magnitude all the way down to the lowest levels, is to do reversible computing in some form. And people say, well, what about quantum computing? Don't get me wrong, quantum computing is great. I wrote a chapter on it during my dissertation work, but quantum computing really only helps for certain problems. It speeds up we have exponentially fast algorithms for certain problems, essentially. Quantum computing is not really designed to be energy efficient on conventional computations. That's not the focus of quantum computer design at all. And, the implementations don't really address energy efficiency. So, so you essentially have to do reversible computing. Maybe eventually, someday, reversible and quantum computing will merge, and we'll have quantum computers that are also energy efficient for classical reversible computations. Okay, so we gave some overview of reversible computing, and I would argue this is really the only way forward in the long term. If we don't want industry to stagnate relatively soon, we have to begin working intensively on sort of making this stuff more practical, fleshing out the designs, going in more depth on the research in general, and to try to make it happen. Before everyone gets used to sort of a state of stagnation in the industry, and I would hate to see that happen, because I think there's a great future ahead of us in computing if we pursue this path. Okay, that's it. Sorry I went over. Yeah.